freestanding wires. You can see that these wires are durable. We can lift off up to 1,000 times their diameter and still have a continuous wire there. If we take that first wire that was copper and now put it across the nickel electrode, we can lift those off, and what we end up with is what's called a crossed bar array. This is the fundamental device that enables memory chips. So being able to address an individual bit between two different circuits. So one wire here and the intersection of another wire determines a unique address. The LCD screens that you have for your computers or your TVs, also use a device like that. So again, here's the energy dispersive spectroscopy showing, in this case, these are nickel wires behind and copper wires in front. We've done these to where there's over 2,100 individually addressable junctions. Taking and making components for thermoelectrics. So I mentioned before how bismuth is a material that is very interesting to physicists, because if they construct this a device out of this, they can take and make something that can either, in this case here, they're using it to generate electricity. So the one side here gets hot, the other side is cold, and it produces a current. You can run this in reverse. You can put in electricity and end up getting cold on one side, hot on the other. One of the components that you need for that is bismuth and bismuth type of compounds, or at least those are some of the most interesting compounds to look at right now. So we're getting ready to publish on this. These are freestanding bismuth wires. We want to take and make bismuth telluride, bismuth lead telluride, a number of other very interesting compounds that are may have applications there. And this is actually a collaboration between our university and the University of Debrecen, which is in Hungary. We have one student in our lab who's doing most of her PhD work in undergraduate laboratory here. So, okay. One of the next really big steps, and this is something that we just took possession of this instrument 3 weeks ago. It's been about 5 years in the back of my mind. It's been a year designing it. We're going to take and make this as a continuous basis. So in the past, we've been using small little electrodes, maybe about 1 centimeter by 1 centimeter, dipping them into baby food jars, and we produce somewhere probably around a femtogram of material. Femtogram is 10 to the minus 15. It's really, really small. So with this device, since we're going to be doing this on a continuous basis, we want to take and make single wires that are over 1 kilometer long. We also want to take and make gram scale quantities of pattern nanowires. And this is something that has never been done. It hasn't been done in national laboratories. It hasn't been done at the big R1 universities. It's happening right here at Stevens Point with undergraduate students. That I think is what's really cool about this. So the design of the instrument here, essentially this is an electrode. It's rotating down into the solution. It rotates down the solution. We electroplate. We bring it up. We blow off the solvent. It transfers over to the edge of another wheel. That wheel then takes and essentially spins off the wire, and it takes and winds it now around this drum. So this is just kind of like a fishing reel, one of the old-time fishing reels, where as you wind it, the little line winder goes across. And so we're looking at taking and making 1 kilometer long wire, hopefully by the end of this semester. So what this tool also does, is it gives us what's referred to as a combinatorial approach. So picture us taking and doing these experiments with the baby food jar. We attach the electrode, we dunk it down into the solution, we apply a voltage. What voltage do we apply? Wow, there's all these different voltages that we could possibly apply to it. And with each voltage, we're going to get a slightly different result. Okay, so now if we want to take and explore that range, we're going to have to take and do many, many, many different experiments. With this, since this is done on a continual basis, and it's being recorded as a function of distance, now we can take and explore a whole huge parameter space. So it gives us a continuous gradient. So something as simple as how fast do we take and turn these electrodes? If we turn it very slow, we give a lot of time for these wires to grow and they're nice and big. As we spin it faster and faster, we can take and make them smaller and smaller. So voltage. So taking and if we grow at very low voltages, typically we kind of get larger, chunkier wires that have crystals embedded within them. There's kind of a certain sweet spot where the nucleation events happen in just right. So it's kind of like looking out across a field where it's just snowed and there's all those little tiny crystals and they all kind of add together to give you nice smooth features. That's what we really look for, but it's kind of tricky to find that. Doing something like this, we can just do a voltage scan as we're going across here and be able to determine what voltage is going to be the best to do. Solution composition. So we've taken and added different amounts of tin into a copper solution. If you take and start off with pure copper, obviously you're going to get pure copper wires. If we have pure tin, we're going to have pure tin wires. Anything in between is an alloy called bronze. And different types of alloys have different properties. So we can take and explore that. Even the pressure to transfer. So we can take and change the pressure to see how well these transfer to the point where we're getting 100% liftoff at a high rate. So at this point, you're probably wondering, what can we do with large quantities of patterned nanowires? And what's Fluffy doing? Sharpening its nails. How is it sharpening the nails? I mean, that's wood. And Fluffy goes up there, rakes the fingernails through the wood, and his fingernails are sharper. Yet I take my axe and I go up to a same piece of wood and try chopping on it. My axe is duller. My pocket knife is duller. Essentially every tool that we've ever made, as mechanically, the more you use it, the duller it gets. But yet there's many examples in nature where the more it gets used, the sharper it stays. So claws, beaks, teeth, all of those, evolution has figured out a way to take and make these tools stay sharper. Why is that? As it turns out, Fluffy's nails are harder in the forward direction than the sideways direction. So when it rakes through the wood, it wears faster from the sides than in the forward direction, and it always maintains a needle-sharp tip. What we're trying to do is we want to take and make metal materials where now we embed within there ultra-hard nanowires going in one direction, combined with kind of like a snowball of softer metal particles that wear faster from the sides. What I want to do is I want to take and make the world's first self-sharpening tool. We're going to do that right here at Stevens Point. Okay, so medical devices. So we've got We've got a collaboration that we're just starting up this summer with the University of Virginia. And these wires here, these thin wires, we want to take and use those as electrodes for living brain cells. Okay, yeah, we don't have FDA compliance for this yet. So what brain are we going to use? A fruit fly. So we're going to be able to take and put these within single cells within the brains of fruit fly. Gives you an idea how small these wires are. Smarter tools. Think about self-sharpening tools. Think about tools that have embedded technology in there that can be identified based upon the circuitry that's within, molded into the plastic. Electronics. So everybody has cell phones, computers, making these things in $9 billion fabrication facilities. Right now, this technology is really at its infancy, but someday, can we just take and make something as complex as a computer chip by dipping into different baby food jars? Security devices. For example, the Oklahoma City bomber was finally caught because there was small little taggants in fertilizer. Taggants are little itty-bitty devices that don't get destroyed in the explosion. So how did they find that? They went through after the building was blown up. They swab all the different surfaces. They take it back to a scanning electron microscope, and they comb through that. And they find these little taggants that eventually they find one, and they're able to identify which batch of fertilizer, which manufacturer, where it came from, and trace it back through. And what I want to do is I want to take and make this so it's an RFID tag. So being able to, an RFID tag is what's embedded in, say, videotapes at the video store. And to be able to have that where it talks back and says, exactly where it came from. Has a unique identification tag to that. Metamaterials. So the military is very interested in this. So metamaterials is invisibility cloak. So the invisibility cloak that Harry Potter has, that actually works, but only at certain wavelengths of radiation right now. And all of that is based off of nanostructured materials. I'm sorry, there is no way that you're ever going to use E-beam lithography to take and pattern the surface of an airplane wing. This technology, I think, can. Smarter materials that detect defects. So if you're thinking about something that is very dependent upon integrity, so something like the fuselage of an airplane, embedding within there little tags that when they're disrupted, their signal changes. So now you put a new one on, you more or less scan it, and it gives you a signal. And then as it ages, and there's these little micro cracks that form within that device, essentially it talks back and says, I've lost about 70% of my structural integrity. Replace me before I fail catastrophically. Thermoelectric devices, we talked about that a little bit earlier. So there's what we have right now is a very, very fundamental technology. And what we're really looking at is a variety of different possibilities. Where the seed grows, I'm not exactly sure. So what does this mean for Central Wisconsin? Jobs. So in the next couple of years, I'm looking at spinning off a business from the university to employ people in Central Wisconsin in a high-tech field. So nanomanufacturing right now is really done either in the Boston area or in the Silicon Valley area, a few little pockets here and there. Central Wisconsin's really not viewed for nanomanufacturing. We want to take and put it on the map. So a spin-off company different products. So the electrodes themselves, looking at educational products to universities and high schools for training. The nanowire product itself, the instrument is a potential product. We've taken and made transmission electron microscope grids, another technological advance that I'm not really talking about here, but we really want to be recognized as a leader in the nation. We want to put UWSP at the center of that. So where do you fit into this high-tech discoveries? From my funding agents. So WISIS, I've received a lot of initial funding from the WISIS Technology Foundation. They've received taxpayer money through the state legislature, University of Wisconsin System, University of Wisconsin-Stevens Point, Argonne National Laboratory. These are all publicly funded institutions. They're open, for example, Argonne, it's open really to anybody to write a proposal and to go there and use the instrumentation for developing the technology of the future. National Science Foundation, and students. So all of this work was really done by students, and so here's my group. It's taken right next door at Green Tea. Every so often we kick back a little bit and have some Chinese food, or we're going to have a cookout this summer. So a couple of final thoughts that I want to leave you with here. So this was the very first transistor, made in 1943, roughly the size of the end of my thumb. Who would have ever thought that back then you'd be putting over 1 billion transistors on a wafer? What can be done in your hometown using the simple electrodes and baby food jars? So with that, I'll close and open it up for questions. Tom.
Mike, actually I have two questions. One is, how do you protect your intellectual property, especially in light of the changes in the patent laws were first filed for, whatever? Do you have all this stuff?
So I've got numerous patent applications in. I've been awarded a couple of patents on this technology. Some of the other ones are pending at this point.
Okay, so you're covered. And my second question is, when you describe peeling back and the star-shaped wires had broken apart because of the bending, is that because the metal was brittle, as opposed to, I think of a lot of metals as having good tensile strength, so I was just curious.
Well, it's a little bit of combination of both. So these wires are ductile depending on the conditions that you deposit them. They can be anywhere from powdery to metallic, and this next summer I have a student that's working on taking individual wires, and we're going to take and press down on them and figure out how much force does it take to break these, and to see what the mechanism is within them breaking. Do they break catastrophically all at once, or is there a whole mess of little slips before they take and break? With that, it's just a matter of, in that extreme curvature, if you take and you curve something, the outside stretches far more than the inside, and it's just those wires really had no chance with the way that we were stretching them there. So.
I'm wondering, can you, or would you do any research on superconductor wires?
So far we've deposited lead. Lead is a superconductor when it gets down to 7 Kelvin. We have not explored the properties of that yet, but that's one of the things that's on my short list. After, actually, I came out of the superconductivity